Alright, let's get started. In our previous topics, we talked about stresses and beams. We did computations regarding the flexural stresses, and we also did computations regarding the shear stresses in a beam. Because as we all know, that when a beam is loaded, and when we say beam is loaded, we are referring to flexural loads, and that means that loads that are perpendicular to this longitudinal axis, let's say this is some arbitrary loadings, that can be flexural loadings, or we can have also concentrated moments. Okay, and when we cut a section right here, what we see are internal forces such as the shear force and also the shear force and the bending moment, right? So because of these internal forces, and if we relate these internal forces to the geometric properties, such as the moment of inertia, then what we see is, or what we get, are stresses. Okay, so one stress is about flexural stress relating to moment, and another stress is about the shear. Okay, however, there's also another response due to these external loadings, and that response is in terms of strains. And when we say strains, this is actually about deformations. Okay, whereas this stress, we can say that it's something about forces, relating to forces, and strains relates to the deformation or the geometry of the material. And when we say deformation, we can actually quantify this deformation in terms of linear, or what we call deflections, and another one is in terms of angular, or what we call rotations or slopes. Okay, this term right here, rotations or slopes, this is often found or often used in beam deflections or flexural members. Okay, but for the deflections, basically when you say deflections, it's all about movements of points. So recall that in an actually loaded members, that if you have this member and it's loaded in tension, and we are referring to this point right here. Okay, so let's say this is our point of considerations, and because of this tensile force, then there's going to be extension of the geometry. Okay, so we have this initial geometry, but because of the force, or because of this tensile force or tensile stress, then there's going to be elongation. And from this point to this point, this is what we call the deflection. Okay, whereas this one, rotations, it's about angular, let's say angular movements of the points. Okay, so now let's just limit our discussions regarding the beam deflections and also beam slopes. Okay, so now going back to this beam, to the simply supported beams, and under some arbitrary loadings, then because of these external loadings, if we are referring to the geometry, then there's going to be changes in the geometry as well, just like in the actual members. We have initial geometry, and then because of the presence of the external loads, then there's going to be changes in the geometry. There's going to be movements of points, and that's going to be deflections. But right here for flexural members, the movements of points, because we have this, let's say we have a downward force, then there's going to be movement of points. Let's say we have this at the midspan, it moves right here, and at this point it moves this much. Okay, so there's going to be something like a curve right here. Okay, so from an initial position of this straight line, let's say this is our initial position. Because of the presence of loads, then there's going to be a deflected position, and this curve right here, it's referred to as elastic curve. Okay, and this elastic curves actually depends upon the loading conditions. If it's a distributed loadings or concentrated loads, or if the direction is upward or downward. So this curve depends on the loadings and as well as in the support conditions. Okay, so if it's a simply supported beams, or if it's a fixed, I mean at this point if it's a fixed beam, so there's going to be changes, or there's going to be difference in the deflections and the slopes. Okay, so the movement of points, we said that this is what we call deflections. And when I say rotations, it's basically the slope at this point right there. So what's going to be the angle? Okay, so slope is the angle, and deflections is just simply the movement of points, linear movements of points. Now, in order to solve these deflections, how much deflections will there be in a given loadings or given conditions, beam conditions? That's going to require computations, and there are actually many methods to solve the beam deflections. And out of the many methods, we'll only consider two methods, namely the integration method, and the other one is the superposition method, or method of superposition. Okay, so before we can delve into the details of the computations, then we have to discuss first the concept of this elastic beam theory. Okay, so in our lecture handouts, there's also sections about the derivations of the differential equations for the deflection curves, but I'd like to discuss it here. Okay, so first and foremost, we have this equation right here. This is equation number 1, and this is actually the moment curvature equation, and we have already derived this in I think we derived this already in the part 1 of the fractional members. And this is just actually the relationship, or something like the force deformation relationship in actual members. But this one, since we're dealing with moments, and the deformation is actually something like a curve, then that's why it's referred to as a moment curvature equation. And where this comes from is from the flexural stress equation formula. We have this my all over I, right? And from the deflected shape, we have this strain given by this E is equal to I think this y all over rho. Okay, so this is strain, extensional strain, and this one is the y is the distance from the neutral axis, and this one is the radius of curvature. Okay, this one is the moment of inertia, and this one is the moment. Okay, so what we can we can obtain the moment curvature equation if we use the Hooke's law. Okay, so if we substitute this value right here and this value of strain right here, what we get is something like this: my all over I is equal to y all over rho. Okay, so since we have both y, since we have y in both sides, then what's left is m. And let's say we'll transpose this e to the other side. So what we get is m all over ei is equal to 1 over rho. Okay, so this is the moment curvature relation, and there's also another way to express this curvature, and this is in terms of the express this deformation, and that's in terms of curvature. Okay, so the difference between this k or this kappa to this rho is this one is the radius, because if we have this beam that curves, for example, because of some loads, then this one, because it curves, and the assumption is that it is a circular curve, and of course it's not that this one is constant, because depending upon the loadings or support conditions, this one can change, right? So the radius, this radius rho can change, and the position of the center also changes along the length depending upon the loadings. Okay, and this k is something like a measurement or a quantification of how much curvy it is, or how sharp is the curve. So something like when you are driving down the road, and if there's a sharp curve, then that's gonna be large k, or we can say, or it is analogous to having a large k. And if you have a large k, then that means that the radius is small, because of this mathematical relationship that it is inversely proportional. But in terms of geometry, it's actually intuitive, because if you have this sharp curve, then of course the radius would be small. But if you have a larger curve, a less curvy, then of course the radius of curvature would be large. Okay, so again, this curvature is something like a measurement, or a measurement of how much curve it is, if it is a sharp curve or less sharp, less sharp curve. Okay, so here's our relationship, and now let's go into our let's go back to our lecture handouts, and we have here, right, the figure 8-3, the geometric relationship of the deflection curve. Now consider that we have a cantilever beam, and that means that this one is fixed, and because of some external loadings, probably somewhere here, because of this external loadings, then there's going to be a deflection. Okay, and if we draw this deflection, of course this is an exaggerated deflection, then the deflection is defined as the distance, actually the vertical distance. So from this point to that point, is this the initial point? It moves here, then that's going to be the deflection. Okay, and right here would be the radius of the curvature, and the slope of the line that is tangent to this curve at that x position, or at that x value, is referred to as the slope. However, when we check the history of this slope and this tangent line, actually it was first derived using the infinitesimal concept, which means that this curve is actually composed of what do you call that, infinitesimally small straight lines. Okay, so it's not really a curve, but rather there's gonna be a straight line. Okay, so that's why you've encountered, or maybe you have encountered the term slope at a point. Okay, so slope at a point. So how come there's gonna be slope at the point? That only makes sense if we think of this curve as as composed of very small straight lines, okay, connected together, or in terms of this tangent line to a curve. Okay, so if we zoom this in, what we see is something like this. Okay, so again, this is the point, and as I've said, since we are as I've said about these infinitesimally small straight lines, it's actually, there's actually a length. The that's the concept here. There's gonna be a length, of course. There's a hypotenuse, and there's gonna be delta x, and there's also a change in the deflection. This one is the change in the position along the x, and we can also relate this curve to the radius of curvature, and also this angle right here. Okay, so now let's consider this curve. So how do we relate this arc length to the radius of curvature, and also this angle? And its relationship is just simply from the basic geometry, that this angle right here, and if we have this arc length and we have this radius, we know that the arc length is just simply equal to the radius times the theta, or the angle. Okay, now what is our arc length if we are referring to this figure? And again, we only consider this one, and this one, okay, for now. Okay, so therefore this will be delta s, right? This is going to be delta s is equal to r. What is r? Instead of using r, we are using the symbol rho, and the theta is just simply delta theta. Okay, however, we are dealing with very small straight lines. Then therefore, if we shrink this down, this delta x to 0, this delta s, this curve becomes actually approximately equal to the delta x. Okay, so that's the concept of the limits, and also the derivative. And so if we replace this by x, then what we get is rho delta theta. And if we rearrange this equation, what we get is delta theta all over delta x. And if we take the limit of delta x, or as delta x approaches 0, what we get here is d theta all over dx. Again, how did we arrive at this expression? It's just simply because taking the limit of this delta theta over this delta x. Okay, so the next thing is, what's going to be the relationship of this delta x to this deflection, and also the theta right here? Okay, so since this is a right triangle, then we can actually apply the trigonometric relations, and we see that this tangent theta is just equal to the opposite all over hypotenuse. This is delta of the deflection all over delta x. But again, since we are talking about very small lines, or very small angles, then the assumption is that the tangent theta is just approximately equal to theta. Okay, right here, the delta s is approximately equal to the delta x. So the curve becomes almost the same as this straight line. It's because we are dealing with very small lines, very small angles. Okay, so therefore we can write that theta is equal to this one. And if we take the limits, what we get right here is theta is equal to d, the derivative of the deflection with respect to x. Okay, so here's our expression now. Now let's relate this to what's going to be the relationship of these two. We have this d theta all over dx, the first derivative, and right here if we take the first derivative of this theta or this slope, then what we get is d theta all over dx is equal to the derivative of the derivative that's gonna be the second derivative of the deflection curve. Of the deflection. Okay, so here's now our relationships, and we can now combine this to our moment curvature equation, and recall that we have this m all over e I is equal to 1 over rho. Now what is 1 over rho? It's just d theta all over dx, right? D theta all over dx. And what is d theta all over dx? This is the second derivative of the deflection. D squared of the deflection divided by dx squared, and therefore if we simplify, if what we want is the deflection and the moment, then we'll use this and we end up with this equation. M all over ei is equal to d squared, the derivative, the second derivative of the deflection with respect to x. So here's now our differential equations for the deflection curves. Okay, so let me write it here. This is the differential equations for the or of the deflection curve. Okay. And now what's the units? The deflection will have a unit of, this deflection right here will have a unit of course, a unit of length. This one, this is moment, and this one is in degrees. And what else? This EI, the product of E and I, the term right here is what they call flexural rigidity. Okay, so anyway, when we do computations, then we can have a wider understanding regarding these concepts right here, and also the units and the terms. Okay, so as I've said, we have two methods, right? Two methods that we'll only discuss here in our course. And before we do that, let's have a discussion about the deflection curve. Actually, let's try drawing these deflection curves for various types of beam conditions. Okay, so actually this is deflection curve or deflection. Let's write it here, deflection diagram. Okay, so how do we draw this deflection diagram? Okay, so in order to do that, let's refer to this table 8-2 about these boundary conditions. When you say boundary conditions, actually you've encountered this already in your course in differential equations. But for us here, when we say boundary conditions, it's the bounds of the moments of the moment functions. Although those bounds actually or usually occurs in this in the supports, but just take note that this one is referring to the bounds of the moment function. So that means that if you have two moment functions in just one beam length, then there's gonna be different bounds, of course. Okay, now let's talk about this deflections and slope at the supports. Okay, so if we have a pin support or roller support, then the deflection, the movement along the y and the x, only the y, the movement of this point is it's actually zero, because we have a support reactions right here, right? There's a vertical support reaction, so therefore it doesn't allow the deflections. It doesn't allow any deflections. But for the rotation, because pin and rollers allows rotations, then there's going to be some value of the slope. Okay, and for the fixed support, since we have reactions right here, vertical reactions as well as moment reactions. Take note, this is moment reactions, this is not internal movements. So because of these reactions, then there's actually doesn't allow any deflection nor slope. Okay, so the slope here will be 0. But for free end, there's gonna be deflection, and there's also gonna be some slope rotations. Okay, so with this concept right here, actually there's still a lot more. Like for example, we have continuous loads, or I mean concentrated loads that causes change in the moment functions. Then there's also tables for that, and they call that as continuity conditions. Now let me show you that, what I mean by that. Here it is. So from the textbook by Craig. This is a textbook by Craig, and right here there's a, what if you have a roller, but this roller is along the midspan, then what's gonna be the deflection at this member, or at this portion, and then what's gonna be the deflection at the other portion. Or if you have a discontinuity in the load function, so right here there is an increasing load, but this at this right segment we have a uniform loadings. Or what if we have a concentrated loads or concentrated moments, so what's going to be the deflections and the slope. Okay, and they term that as continuity conditions. Okay, but for now we'll just focus on these three boundary conditions, and just take note of the deflection. I mean, why is there no deflections in the pin and roller supports? It's just simply because of the presence of the support reactions, vertical support reactions. But because they allow rotations, then there's going to be value of some slopes. And for the fixed supports, because all three reactions are present, then there's going to be no deflections nor slope. Okay, so now let's try to draw. Let's say we have this simply supported beam. Okay, and we have this concentrated load. Then what's gonna be the deflection? Okay, so take note, this is a beam, this is a roller. There is no deflection, but there is rotation. So the deflected shape would look something like this. Now what if we have a fixed support, right? So we have a fixed support beam or fixed end beam. Then the deflection would be, because right here there's no deflections and there's no rotations, then we have this, or we can just draw it something like a straight line, and then it curves like this. Okay, and we have a maximum deflection right here, but I forgot to draw the loading, so we have this uniformly distributed loads. Okay, now what if we have a cantilever beam and we have a loading right here? Then the deflection would be, again, since this is a fixed support, then there's gonna be no deflection and no slopes. But right here we have a maximum deflection at this end. Okay, then another one is, what if we have this something like a simply supported beam but with overhangs? And we load it right here, then what's going to be the deflections and slope, or what's going to be the curve, right? So right here, because this goes down, then of course there's going to be, or the deflection would look something like this. Okay, but since there's no loadings in this portion, then it will continue like this. But since because of the presence of the supports, it restrains back again, and it will look something like this. Okay, what else? Okay, now what if we have this this fixed support, and right here we have a roller support, and right here we have an internal hinge, and this one is a pin. Okay, so what if we load it in this portion? Then the deflection would look something like this. Again, this is just a straight. Okay, and then this will just continue until it gets to this internal hinge right here, and then it actually releases the moments, because this internal hinge, they are internal release. Okay, so it releases moments at this point, and therefore it's not continuous. And finally, if we have this beam loadings loaded right here, and then loaded this point, then sometimes if it's hard to draw the deflection diagram, sometimes it is helpful to draw the moment first. Okay, so the moment here would the moment diagram would look something like this. And right here is a positive moment, and right here is a negative moment, and therefore now, since we know the moment, the sign of the moment, then we can draw the deflection diagram. So it will look something like this. Negative moment means that the deflection, or the curve, I mean, it curves downward, and if it's a positive moment, then it curves upwards. Alright, so I guess that's all for this video, and in the next video we will start discussing the integration methods, and we'll do a couple of computations regarding that. Okay, so see you in the next video.